Today we study Y23 Lorentz Transformation. We learned that an object, motion of an object can be expressed in terms of event. Event represents the space-time position of an event. So this is a Euclidean three-dimensional vector that describes sorry about that. So this is a position vector for the spatial coordinate, and this is the position in time, because the dimensions of time and position are different. So we multiply a constant speed of light to the time. If the position does not change from the beginning to the end, in that case, the time coordinate is expressed in terms of tau, and this Greek letter tau represents the proper time. Proper time. If an object moves, these two events are the same, but if this object moves, then the position can be expressed as the product of velocity multiplied by time. And this time appears in the time coordinate too. However, this time is different from the proper time tau, that is gamma tau. This is what we learned in the last class, the time dilation. Let's see, this ball and this ball, they are the same ball. However, we are describing this motion in the frame where the ball is at rest, number one. If we look at this system in the frame where ball is at rest, the coordinate does not change. Only time changes, but that time is proper time. Instead, this ball is passing through a box. You can see the length of this box and the length of this box looks different. The reason is that in the frame where ball is at rest, this ball is at rest, but this box is moving along the direction of longitudinal direction, that is the relative velocity. The box is moving with minus v along the x-axis. The length of the box along the x-axis shrinks. That is called length contraction. On the other hand, if you describe this motion in a frame where box is at rest, then the ball is moving. Box has the length L0 in the frame where box is at rest. We say this L0 is a proper length. The proper length of the box that is measured in the rest frame of the box can be measured by measuring time consumed by the ball from this point to that point. You can see the diameter of this ball is still the same. However, along the direction of motion, it became pizza-like shape. So the diameter along the longitudinal direction has been shrunken. Okay, so this is due to the length contraction, time dilation, and length contraction. Ball becomes smaller along the direction of motion. In the frame where ball is at rest, the length of the box shrinks by a factor of 1 over gamma. That is square root 1 minus v squared over c squared. This is what's going on in special theory of relativity. The length contraction, let's recall the proper length. Proper length, proper time, it is always measured in the frame where an object is at rest, it does not move. Box moves backward in the frame where red ball is at rest. Red ball moves with the same magnitude but opposite direction in the frame where the box is at rest. We describe two events: when the ball enters the box, and event B, when the ball leaves the box. And we have two observers. One is at the ball's rest frame, the other is at the box rest frame. Okay, event A is synchronized. We put 0 stopwatch fixed at ball's rest frame and another stopwatch fixed at box rest frame. They were synchronized to be indicating 0 at time. And then we measured event B when the ball leaves the box in these two different frames. The length of a moving box, what should I do? L equals V tau. Measuring the length of the box in the frame where ball is at rest, you have a stopwatch. Fixed that does not move relative to the red ball. So you measure time. This time in the frame where ball is at rest, you have time. This is tau instead of t. By measuring tau, this is tau. When the ball leaves the box, you can measure this tau, and here it used to be 0. From 0 to tau. What happens? To the ball, box has been moving to the negative x-axis with the relative velocity v, right? Therefore, if I want to measure the length of the moving box with the velocity minus v, the time, proper time that I measure fixed to the ball can be used to measure the length of the moving box. Proper time multiplied by velocity. On the other hand, if I want to measure the length here in the frame where the box is at rest, what should I do? I know the ball is flying with a velocity plus v, and the position of the ball changes. Therefore, the time that I measure in the boxed rest frame is not tau, instead we measure time called t. And with the time t, the ball has been flying with the same uniform velocity capital V. Therefore, if I want to measure the length of the box in the rest frame of the box, L0, that is the proper length of the box, that is V times T instead of V times tau. So we have a discrepancy of the two lengths. Actually, this T is gamma tau, always greater than tau. Therefore, this is L0 is greater than L. So L is the length of the moving box measured in the ball rest frame. That is gamma L. Therefore, if I want to measure the moving box length, that is L0 proper length divided by gamma. That can be expressed like that. Therefore, any moving object shrinks with a factor, multiplicative factor, 1 over gamma, that can be expressed in terms of square root 1 minus beta squared, where beta is the velocity divided by speed of light. And actually, this length contraction derives directly from the time dilation. So length contraction and time dilation, both concepts are consistent with each other. So a relativistic flying ball, if it is at rest, if velocity increases, the diameter along the longitudinal direction shrinks by a factor of 1 over gamma, that is square root 1 minus v squared over c squared. Remember that transverse direction that is perpendicular to the motion is invariant. That does not change. Okay? The consequence of length contraction and time dilation, there are many. And the time dilation is not a fake, it is experimentally measured. And you can click the links and you will find a very interesting information regarding GPS. GPS is the global positioning system that we use every day. Your cell phone or when you drive a car, and this GPS relies on relativity. If we turn off the relativity, that includes both special theory of relativity and the general theory of relativity that governs the gravity. If we ignore Einstein's relativity in GPS, the information is completely wrong. Every day, GPS will give errors greater than 10 kilometers every day. So, if this is not a joke, relativity is reality, and every day you are using relativity, regardless of the fact whether you understand what relativity is or not. So based on the information, what we have found, we can re-describe Michelson-Morley experiment in a correct way. Previously, we studied the motion of a transverse light wave However, the longitudinal motion of light is rather complicated. However, now we can do the correct job. Let's see. This is, and actually we had an experiment. We have two arms of length L of a proper length L0 in the rest frame of the Earth. And this device, as well as the Earth, moves with the velocity capital V. In that case, light traveled back and forth, light traveled back and forth. We computed this one in the moving frame, and we saw that the motion is a Vt, and this is a Ct, and this part was a C tau, something like that. So using this idea, and this C tau is invariant as the length of the arm, L0. Using this, we derive the fact, the time dilation. And because of the time dilation, we have shown that the length contraction appears like that. So we apply this longitudinal motion. In the case of transverse motion, time required for the travel forward and backward, they were the same. However, in this case, time required for the travel to meet, so this is the starting point, and then this device flies with the velocity v, and this guy flies with velocity v. So when it reaches the mirror on the right hand side, this point B, this was A, O, when it reaches this point, this mirror has flied by v times time forward. The light travels with the speed of light, so this length is longer than what the mirror has flied. And this light catch up with this mirror and they meet. And when it returns backward, still this whole device is flying. So when it returns, we need to consider the motion of this whole object forward. So it needs a longer time for the travel to hit this mirror. However, when it returns, it needs less time. That is the basic idea. In addition, when the box is moving in the frame where we are stick to either rest of frame or actually either doesn't exist, so the sun's rest of frame, something like that. In that case, the length of this whole device shrinks by a factor of 1 over gamma. That is square root 1 minus beta squared. Okay, using all of this fact, look at this. This one is a sum of these. Sum of these two is this. And we have a simple algebra for forward time and backward time. And round trip travel time, that is a sum of forward time and backward time. At the end of the day, the final result shows that this time, what's that? This is the proper time required for the travel when the mirror is not moving. However, this whole device is flying with the speed of velocity v. We have additional factor that respect the time dilation. So is it something like tau? and something like t. Remember, any moving object is described by the time t instead of tau, and the spatial coordinate is vt, and time coordinate is ct. If something is at rest, it can only be expressed in terms of proper time, c tau 0, 0, 0. All right, so this is the whole nature of the time dilation and length contraction. Based on these two observations, we can find the space-time coordinate transformation rule that is called the Lorentz transformation. We have two frames of reference, the fixed to a particle. Here we have proper time only, and the frame x prime is measured in a frame when object is moving with the velocity v. Okay, so just like what we have done with the rotation matrix, we can find what the matrix representing the Lorentz transformation that results in the time dilation and length contraction. It's easy because we multiply this one to an unknown 2 by 2 matrix. The answer must be this. That's what we already proved. So using this fact, we can determine the first column of this 2 by 2 matrix. The result is gamma and beta gamma, where beta is V over C. Einstein's relativity states that just like Newton's third law of motion, inverse transformation of this transformation matrix can be obtained by flipping the sign. Why? Two objects A and B are moving with each other. If the relative velocity of A is V, then the relative velocity of B measured by A is the same as V except for the sign difference. Therefore, the matrix for the inverse transformation from A to B to B to A, they have reciprocal relation as long as we replace the velocity by minus V. In this manner, we can determine the other two elements, and the details of the calculation is given in here. Finally, we have determined the matrix for the Lorentz transformation is of this form. An inverse can be obtained by replacing V with minus V. That is this, because gamma is independent of the sign of beta. It is always squared. As a result, we can find the inverse can be multiplied to find that product is identity matrix that returns to the same thing. It is a very similar but different from what we usually find for the rotation matrix that is also diagonalized when we multiply the rotation matrix R theta inverse and R theta. In that case, we use to find cosine squared plus sine squared, cosine squared plus sine squared, and 0, 0. And what's that? It was 1. However, while this sign is a positive in the Euclidean space, the space what we are considering for the four-dimensional object called 4 vector is not positive but negative. That means square, gamma square subtracted by gamma beta square. This is 1. Here, plus is 1. Therefore, we can make use of a very simple mathematical relation. By the way, just by applying this 2 by 2 matrix and keeping the y and z components that are transposed relative to the motion, we can find out explicit transformation rule for space-time coordinate. These transverse components are invariant, and longitudinal component and time. Time also varies. It is distinguished from Galilean transformation that describes Newtonian mechanics. So time varies as well as the coordinate varies. And there is overall factor that is called the Lorentz factor. This one makes this relation very complicated. However, what we find that gamma squared minus gamma squared beta squared is 1. This one makes a great simplification. For example, the coordinates, space-time coordinate of event B in the frame, box rest frame, CTVT, C tau, it is a ball rest frame. These two look different. However, just like this, square of time component subtracted by the square of the spatial component is always the same as the original value measured in another inertial reference frame. Therefore, this relation is strongly supports the new invariance, the invariance of 4 vector that is called, that for example, this event of a particle expressed in relativity is different from Euclidean space, whose scalar product is just positive everywhere. Instead, the scalar product in the Minkowski space that is described by this strong relation constraint. Scalar product is time component product subtracted by the scalar product of the spatial component. So this is a big difference in the sign change between the time and space results in an absolutely different nature, just like the time dilation or length contraction. So we define x squared. This is not the second component, but x squared of a 4 vector. 4 vector means we have 4 components here. Euclidean 3 dimension and time dimension. It consists of 4 components. So we use a 4 hyphen vector that represent the 4 component vector described by this invariant quantity. So square defined by this is invariant under any Lorentz transformation. So while we have 3 vector that has an invariance of radius squared on the rotation, a 4 vector is invariant when we calculate the scalar product in this manner. So, for example, we have a right triangle. In the Euclidean space, radius is invariant. Then we can draw a circle, and these points represent the coordinates of a point on a circle. In here, R is invariant. However, in the Minkowski space, this hypotenuse is not invariant. Instead, this opposite side, this guy is invariant. As you can see from this right triangle, this side can be computed by squaring this, subtracted by square of this, and take the square root. So this is the invariant quantity in relativity. instead of hypotenuse. Therefore, the scalar product can be expressed in such a manner, we have to put the negative sign on it. This is for the Euclidean space. We have a metric tensor because this scalar product can always express as a product of row vector and column vector. And by inserting the identity matrix between these row and column vector, I don't have any difference at all. However, in the case of Minkowski space, we have a negative sign in the product between the spatial component. So time component, spatial components. Spatial components have additional negative sign. Therefore, while the Kronecker delta, that identity matrix, is inserted to find out the scalar product in Euclidean space, in Minkowski space, we need a negative sign in the spatial component. So this usually we use a G, that is a metric tensor of the Minkowski space that describes the transformation of a full vector. So previously, I introduced the angle for the rotation. However, our constraint that gamma squared minus gamma beta squared equals always 1 requires new parameterization such as hyperbolic function. So you remember, as far as the cosine hyperbolic and sine hyperbolic, we have negative sign. It is always satisfied. Therefore, our new parameterization for a Lorentz boost is cosine hyperbolic is gamma, sine hyperbolic is beta gamma. Okay, why don't we take the ratio? Then gamma cancels and beta, that is a V over C, appears as a tangent hyperbolic. If you look at the time and longitudinal component only, in that case, the Lorentz boost matrix looks like that, and we can pull this common factor gamma out. In that case, it becomes a 1 beta beta 1. In the limit, as V goes to C, we will find that beta is V over C, it reaches 1. In that limit, when a particle is extremely boosted to the speed of light, that the transformation matrix approaches 1, 1, 1, 1. In addition, we can repeat the boost by many times. And just like what we have done with the rotation matrix, we can simply multiply the two boost matrix. It looks busy, but it is very simple. What's that? This is cosine hyperbolic sum of the two parameters. And this is a sine hyperbolic sum of the two parameters. And these are the same. Remember, rotation looks like cosine sine minus sine cosine. And its determinant was 1, cosine squared plus sine squared. In here, still the determinant is 1, the same. However, we have a hyperbolic. So cosine determinant is a cosine squared minus sine squared, a hyperbolic squared. So it is determinant is a positive 1. Using this idea, we can find that the product of two boosted consecutive boost along the same axis result in a new boost with the parameter, sum of the two parameters. However, if you add this tangent hyperbolic, this one represents the relative velocity. This is V over C. What is the resultant relative velocity after a series of boosts? That the rule for the sine and cosine hyperbolic function can be used to find like that. We remember this is a V over C for the first and V over C for the second, and substitute all of them. Aha! This is the sum of the two velocities divided by 1 plus the product divided by speed of light. So when you add to the same velocity, then you will find 2v over 1 plus v squared over c squared. This additional term in the denominator changes the final, rescale the final value. Extreme case, you can substitute the speed of light in here. The answer is 2c over 1 plus 1. That is c. So if you boost by the speed of light and then boost again with the speed of light, the single boost from the original place to the final is not 2c. It is impossible. It is always the speed of light. It is the velocity addition formula for the relativity. This one respects the speed of light cannot be exceeded by any particle's motion.